Section 3, Real Numbers in the Number Line. The square root or a radical, if you'll notice, this says the square root of 64. This is the square root symbol, or the radical symbol. It kind of looks like a division symbol, but you notice that it has the little check mark in front instead of just being a straight line. So that we read that as the square root of, and the number inside is called the radicand. So in this case, our radicand is 64. If we're wanting to simplify or solve a square root, we're asking ourselves what number multiplied by itself equals 64. So if you think about it, 8 times 8 equals 64. 64 is called a perfect square because a whole number times itself equals 64. So in this case, the square root of 64 is 8. You should have seen square roots before, and you can make a list of perfect squares by just squaring. Usually I say 1 through 20. So if you can make yourself a list and just do 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, and so on. That will help you when you're trying to find the square root of numbers. What is the simplified form of each expression? So this is asking us, A, to find the square root of 25. Well, what number times itself equals 25? If you have that list that I just spoke of, you can see very quickly what the square root of 25 is, or what number times itself equals 25. If you haven't made the list, then you're going to have to just think to yourself, 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, I'm getting closer, and 5 times 5 will give you 25. So the square root of 25 is 5. Now, B, for the radicand, I have a fraction. When we have a fraction inside of our radical symbol, we can actually break it up, and we can take the square root of the numerator, in this case 4, over the square root of the denominator, in this case 81. So we can break it up like so. Well, the square root of 4 is 2, and the square root of 81 is 9, so now I can write it as 2/9. So when you have a fraction inside of your radical symbol, break it up and take the square root of your top number over the square root of your bottom number. This asks us to approximate the side length of a square that has an area of 220 square inches. If you think back to how you find the area of a square, you take the side length and you're going to square it. So area, or A, equals S squared, where S is the side length of a square. Because we are told that the area is 220, we can plug 220 in for A, and now we have 220 equals S squared. If you think back, I need to get S by itself. So I need to solve for a single side length. If you think back to your inverse operations, the opposite of addition was subtraction, the opposite of multiplication was division. Think to yourself, what could the opposite of squaring something be? And the inverse of squaring is taking the square root, and just like our other inverse operations, whatever we do to one side, we have to do to the other. So I'm going to take the square root of S squared to get myself S, and then I also need to take the square root of 220. If you've made your list of perfect squares, then you quickly see that 220 is not a perfect square. The question asks the approximate side length. which indicates that I am going to be estimating or finding the closest answer. If you have made that perfect square list, you can see that 14 squared is 196. So we're getting really close to 220. And then check 15 squared also. 15 squared is 225. So the closest or the best approximate side length would be 15 inches. Talking about rational numbers, a rational number is any number that can be written as a fraction and has a decimal form that is either terminating, which means that it has a stopping point, or repeating. If you remember, 1/3 is a great example of a repeating decimal. 1/3 gives you 0.333333, and you can keep going on and on forever. If you remember bar notation, that way we can write 0.3, and we draw a horizontal line over 3, which means that 3 is going to keep repeating on and on forever. Those would be examples of rational numbers. A natural number, these are sometimes called counting numbers. They are positive whole numbers that are greater than 0. Examples of natural numbers would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And notice I have ... So you could keep going past 10. It's any positive whole number that is greater than 0. So 0 is not included in natural numbers. Whole numbers are positive whole numbers that are greater than or equal to 0. So whole numbers are actually going to be all the same numbers as natural numbers, but now it does include 0. So we're going to start at 0, and we can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and keep going up from there. Those are examples of whole numbers. So the difference between natural numbers and whole numbers is that natural numbers do not include 0, but whole numbers, it does include 0. Integers are positive or negative whole numbers. So integers are not fractions or decimals. They're going to be positive or negative whole numbers. So if you notice, I have ... which means that I could keep going on and on and on in the negative direction. And then I have -5, -4, -3, -2, -1. 0 is included. 1, 2, 3, 4, 5, and I can keep going on and on in the negative and the positive direction as long as they are whole numbers. An irrational number cannot be represented by a fraction, and decimals that do not terminate or repeat. A great example of an irrational number is pi. We usually learn pi, and we only learn it to 3.14, but pi actually keeps going on and on forever, and there's no pattern. It doesn't repeat, and it does not ever stop, so it does not terminate. Another example of an irrational number might be 0.10100100001, and notice I have a ... which means that it did not terminate. It didn't stop at that last one. It's going to keep going on, and there's no repeating. Which subsets of real numbers does each number belong? A is 12. 12 is a rational number. It's also a natural number. It's a whole number, and it's an integer. If you look at B, it says -5.01479. Notice that there is nothing after 9. If it was going to keep going on and on forever, it would have a ... Because it does not have 3 dots at the end, it means that it does terminate. It does stop at 9. So it is a terminating decimal, which makes it a rational number. And then if you plugged in, for C, if you plugged in the square root of 21 into your calculator, you would get this really, really long number that keeps going on and on and on. It's going to be 4 point something, 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 and it's never going to stop, and there's no repeating going on, so we call it an irrational number. Inequality signs, these should look familiar to you. We have the less than sign, we have the greater than sign, we have less than or equal to, and we have greater than or equal to. To compare two numbers, they have to be in the same form, which means they all have to be decimals, or they could also be fractions with the same denominator. If you're making them all in fraction form, they have to have the same number on the bottom of the fraction. This asks us to write an inequality that compares the numbers, the square root of 34, and 5 4/5. If you notice, they are not in the same form. I have a radical or a square root, and then I have a fraction. It's not going to be very easy to get my radical to a fraction, so I am going to change both of these to decimals. I will let you use a calculator to find the square root of 34. When you plug it into your calculator, it's 5.83095. Notice I put a dot, 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 which means that it is not terminating. It's going to keep going on and on and on. To change 5 4/5 to a decimal, it is 5.8. To compare these two numbers, the numbers that follow my 5.8, we could fill in zeros past there. It's just 5.8000000. So when you're comparing them, both numbers have 5 in the 1 spot. Both numbers have 8 in the 10th spot. But when you move over to the 100th spot, the square root of 34 has 3 in the 100th spot, and 5 4/5 would have a 0 in the 100th spot. So when I'm writing an inequality that compares the numbers, the square root of 34 is going to be greater than 5 4/5. Notice that when I wrote my inequality, I went back to the original form. So instead of using 5.83095 dot, 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 I went ahead and I put it back as the square root of 34. That's important. When they're asking you to compare two numbers or multiple numbers, you need to always go back to the original form that they gave you in the problem. The last example asks us the order of the square root of 9, 3/10, -1/4, the square root of 3, and -4.25 from least to greatest. If you remember, negative numbers are always less than positive numbers. And negative numbers, the bigger the number, the smaller it actually is when you're talking about negative numbers. If you notice, I have radicals or square roots, I have decimals, and I have fractions. Before I can compare these, I need to get them all in the same form. So take the square root of 9, and I'm going to try to put it in decimal form. Well, 9 is actually a perfect square. 3 times 3 is 9. So the square root of 9 is 3. 0.3 is already a decimal. I don't need to do anything to it. -1/4 is a decimal, is -0.25. The square root of 3 as a decimal is 1.73205. And -4.25 is already in decimal form. Now I can order them from least to greatest. My largest negative number is -4.25, so it's going to be my smallest number. Then I would have a -1/4. The next smallest number would be the positive 0.3. Then I would have the square root of 3, and finally the square root of 9. Again, notice that when I ordered them, I put them back in their original form. When you have a group of numbers like this, it's always a good idea to go back and count and make sure that you've ordered the same number of numbers that they gave you in the problem. So in the problem I had 5 numbers, and in my answer I should have 5 numbers. That's just a quick way to prevent silly mistakes. The assignment for this section is on page 23. It's numbers 10 through 52 even.